So today we're going to take the next step in our understanding of stoichiometry and talk about the idea of limiting reactants. What is a limiting reactant? So to introduce this concept, we're going to start with a non-chemistry analogy. Let's say you work in a factory and you're building cars. And on the factory line, you notice that you have 8 car bodies coming in to make cars move. Okay? So one pile you got 8 car bodies. In another pile you have 48 tires. And your job in the factory is to put the tires onto the cars so they can be rolled out and sold to whoever they're going to. Well, we know that one car needs 4 tires. Okay? So let's think about how many cars we can make. Well, 8 car bodies. If each car needs 4 tires, and I have 48 tires, how many cars could I make with these tires? Well, 48 divided by 4 would give me 12 cars. So I have enough tires to make 12 cars, and I have enough car bodies to make 8 cars. So what's the maximum number of cars I can make? Well, the maximum number of cars I can make is actually only 8 cars, because once I run out of car bodies, I don't have any new bodies to put the extra tires onto. So in this case, we would say, in this reaction, our car bodies are our limiting reactant. So that's a key vocab term we need to know. The limiting reactant is the reactant that gets used up in the reaction. All of it gets consumed is another word you'll hear. Another word for reactant that we need to be familiar with is reagent. Reagent and reactant mean the exact same thing. So since our car bodies are limiting, that means we're going to have some extra tires left over after we've made our 8 cars. Okay? So our tires in this case are not our limiting reactants. They are actually called our excess reactant. And again, the word reagent is sometimes used as well. We need to be familiar with both terms. 2 key vocab. The limiting reactant is what gets completely consumed or used up in the course of a reaction, and the excess is the other reactant that you have left over of after the reaction. So in this case, how much excess reactant would we have? Well, if we used 8 car bodies and each car body needs 4 tires, how many excess tires are you going to have? Well, if each one needs 4 and you have 8 bodies, that's going to be 32 tires get used up. Our initial amount was 48, so if we use 32, our excess number of tires would be 16 tires in excess. So what I just did there is I solved 3 different types of problems. We first needed to identify what is the limiting reactant. Second of all, we wanted to figure out what is the total number of, or total amount of products, in this case cars, we could make. And we also wanted to figure out how much excess reactant would be left over, assuming this reaction occurs. So now let's translate this concept into a chemistry setting. So, here's an example equation. A 2.00 gram sample of ammonia, which is NH3, is mixed with 4.00 grams of oxygen, according to the reaction below. What is the limiting reactant? Okay, so we're not dealing with cars or car bodies anymore. We have to figure out which molecule, nitrogen or oxygen, is going to get used up first. Now, most common mistake students make is just looking at the mass. thinking, oh, I have less ammonia because there's 2 grams of it than oxygen, so ammonia must be limiting. The problem with that is we don't deal with mass when we're doing quantitative problems in chemistry. We always use moles. So what we need to figure out is which compound, this is your key question to figure out, which compound is going to involve fewer moles, less moles. So what we have to do is we have to figure out how many moles of each are going to get used up in the reaction. So let's just start with our 2-gram sample of ammonia. This is going to be using our gram to gram knowledge. So 2 grams of NH3. We know using the periodic table the molar mass of NH3 is 17 grams, 1 mole. So that would be how to convert it to moles. But the problem is we're not done here because we know the mole ratio also plays a role. For every 4 moles of ammonia that are consumed, only 3 moles of oxygen are consumed. So we have to use that knowledge in our problem solving. So what the next step is to choose a reactant. Choose a product. Choose a product to convert to. So it doesn't matter if we choose N2 or H2O. It doesn't matter. Pick whatever one you want. Let's choose N2. So 4 moles of NH3 is going to produce 2 moles of N2. So if we do the stoichiometry and we do the math for this, we're going to get 0.0588 moles of N2 produced. Now we got to do the same thing for oxygen. So for oxygen, we're given 4 grams of O2, 32 grams in 1 mole of O2. We got to figure out how many moles are going to get used up. So we do the same thing. We do 3 moles of O2, and we got to use the same product as before, 2 moles of N2. And if we do the math for this, we get 0.0833 moles. So clearly, if both ammonia and oxygen are reacted, the one that's going to produce the least amount of product is going to be ammonia, because the number of moles of product produced there is less than that of oxygen. So we would say that NH3 is our limiting reactant, and that O2 is our excess, meaning there will be extra oxygen left over when this reaction finishes. Let's do more complicated problems now. In this case, we have 90 grams of iron chloride reacting with 52 grams of hydrogen sulfide. What is the limiting reactant? Same problem as before. Take our 2 reactants, 90.0 grams of FeCl3. We got to convert to moles of one of the products. So I'm going to stop here and think, are there any other follow-up questions here? Oh, part B asks, what's the mass of HCl produced, one of the products? So I'm going to use that as my last step because it's going to save me some time. So I'm going to go from grams of iron chloride, it's 161 grams per 1 mole. And then from the equation, I have 2 moles of FeCl3 produces 6 moles of HCl. So how many moles of product would I get here? About 1.677. What if I did it with 52 grams of H2S? Well, in this case, I'm going to do the same conversion. 34 grams is 1 mole. From the mole ratio, it's 3 moles of H2S for every 6 moles of HCl. And that's going to produce 3.04 moles of product. So clearly, I'm going to make fewer moles of product with iron chloride. So this is going to be my limiting reactant. We just answered part A. Therefore, by definition, H2S, hydrogen sulfide, is my excess reactant. Now part B asks, what is the mass of HCl produced? Well, I know I'm going to make a maximum of 1.677 moles of it. So let's just convert that to grams. It's mass. 1.677 mole of HCl. Convert it to grams. 1 mole of HCl is about 36 grams. So if I do that stoichiometry, I should get about 60.4 grams of HCl produced. This means I'm going to have some leftover H2S, because it's the reactant in excess. And that's actually what part C asks. Part C says, what mass of XX reactant remains after the equation? Well, if we go back to the problem, how much did we start with? We started with 52 grams. So I started with 52 grams of H2S. We want to know how much is left over. So to figure that out, I need to know how much did I end up with. How much did we, in order to figure out how much we ended up with, we got to figure out how much did I use. So to do that, we got to do a little stoichiometry again. We know that all of the iron chloride got consumed. So 90.0 grams of iron chloride was consumed. So let's do a grams to grams conversion to figure out how much H2S would have reacted with all of this. So grams to grams, okay? First convert to moles. There's 1 mole of FeCl3. Now I got to do my mole ratio step. So 2 moles. This is from the equation, FeCl3 for every 3 moles of H2S. Again, just to refresh yourself, those came from the coefficients in the equation. Convert it to grams, 1 mole of H2S is 34 grams. So what does that come out to with the math? It comes out to 28.5 grams of H2S. So just pause and think, what does this actually mean? This means that since FeCl3 is the limiting reactant, all of it gets used up. It's like the car bodies. All the car bodies get used up. The H2S are like the tires. Not all of them are going to get used. We're going to have some left over. In fact, only 28.5 grams out of the 52 get used. So how much is left? Well, it's just the difference between the two. So 52 minus 28.5, what we started with minus what we used, is going to leave us with 23.5 grams of H2S in excess. So if you looked in your beaker or in your reaction vessel, you would have some H2S left over. All of the FeCl3 would be consumed, and the amount of product you have would have been equal to 60.4 grams of HCl. Key points to walk away with. You need to know the definition of a limiting reactant, an excess reactant. You also need to know that the term reactant and reagent mean the same thing. You need to know how to find the limiting reactant. So if you want to refresh that, watch part A again. You need to know how to figure out the mass of one of the products. If you need that, watch part B. And you also need to know how to figure out how much excess reactant remains. This is all basic stoichiometry, conversions between grams, moles, grams to grams, but thinking about it a little more conceptually.